All right, so let's start. So today is the second part of chapter 5 lecture, and here we are basically going to learn about the gravitational force. I mean, details of the gravitational force and how satellite orbits around our Earth, around our planet. Okay. All right, so in last lecture, basically we talk about the uniform circular motion. So uniform means the magnitude of the velocity is constant in the circular motion, okay? But sometimes the velocity may not be uniform, right? I mean, the magnitude of the velocity may not be constant. Okay, so what happen if the magnitude of the velocity or the speed is not constant? Okay, so if the speed is not constant, we call it non-uniform circular motion. So by its name, if you see that it is non-uniform circular motion. So non-uniform means speed is not uniform or constant. Okay, so here in this picture you can see that. So the direction of uh, the the direction of the velocity, okay, is the green. Okay, so the green means the direction of the velocity, and here you see that the velocity, the length of the green arrow changes. Okay, so you see that it's different. Okay, so when we have a non-uniform circular motion, or when the speed is not uniform in a circular motion, then we have two types of acceleration. Okay, one is centripetal acceleration, very similar to what we see in the uniform circular motion, and its definition is still this. Okay, centripetal acceleration equal to v square over r, but on top of it we'll have a tangential acceleration. Okay, so the tangential acceleration, so here you see that AC means AR. So I copied this from another document, so where they use C subscript for the centripetal acceleration. So but it's the same thing. AR or AC is the same thing. So the direction of AC is this one, okay, which is to the center of the circular path. And in addition, we have a tangential acceleration. And tangential acceleration is basically due to the change of the magnitude of the velocity. Okay, very similar to what we see in chapter 2. Okay, so we have an acceleration to the center of the circular path, and another is tangential to the circle. Okay, so here you see at any point we have two acceleration. Okay, so if you think about this point, so this is the centripetal acceleration and this is the tangential acceleration. This is the centripetal acceleration, this is the tangential acceleration. So centripetal acceleration is along the radius, okay, and the centripetal acceleration is along the radius, and tangential acceleration is along the tangent. So this angle, the angle between the centripetal acceleration and tangential acceleration, is always 90 degrees. So this angle is always 90 degrees. Okay. So because they are 90 degree, okay, from the knowledge of chapter 3, if you want to know what is the net acceleration, so we have two components of the acceleration here, right? One is this one and another is this one. So if you want to know what is the net acceleration, you can find the magnitude and the direction by using the knowledge you already learned in chapter 3. Okay, so what is the magnitude? Magnitude will be this. Okay, so the magnitude will be this one, which can be determined using the Pythagorean theorem. Okay, because right, this and this, the direction of the net acceleration will be this. Okay, and because this and this are perpendicular to each other, 90 degree. Okay, you can find the length of this one by using the Pythagorean theorem. Why? Because this is exactly same as this, right? So you see that this is a right triangle. Okay, so we know the length of this one, we know this acceleration, we know this acceleration. So by Pythagorean theorem, we can determine this net acceleration. Okay, so that's the equation I show here. All right, so that's about the non-uniform circular motion. Now let's move on. Now we are going to learn about gravitation, more on gravitation. Okay, so in chapter 4, we learn we learn a little bit about the gravitation, right? We know that if we have an object, if its mass is m, then the gravitational force is, so if we have an object of mass m, the gravitational force is Fg, that is equal to m times the gravitational acceleration. So that we learn in chapter 4, right? And the direction of the gravitational force is always to the always downward. Okay, so so if we are here, so let's say this is the earth. Okay, so if we have an object here, the direction is in this direction, right? All right, so that we already learned in chapter 4. Now we are going to learn gravitation in a little bit different way. Okay, now the law we are going to learn is called the Newton's law of universal gravitation. So Newton basically give us this law, how two objects basically attract each other. Okay, so let's say we have two objects, one is m1, another is m2. M1 means the mass of this object is m1 and the mass of this object is m2. Okay, and the distance between the center of m1 and center of m2 is r. Okay, so this is the distance between the center of the objects. Okay, so you see this is the center, so we are measuring the distance from the center. Okay, so remember that here in this chapter, when we deal with two objects, okay, if they are not too small, when they are small, very small, then it doesn't matter whether you are measuring from the center or from the edge. But when the object has some size, okay, we have to measure the distance from the center. Okay, so if the mass of the object 1 is m1 and the object 2 is m2, then, and if they are separated by distance r, experimentally found that the force between these two objects is proportional to m1 and m2, the product of m1 and m2. Okay, so what it means? It means if m1 is large, or if m1 or m2 are large, or both are large, there will be large force. Okay, the force between this m1 and m2 is proportional to product of m1 and m2. So you can increase, okay, you can increase the value of f by increasing value of either m1 or m2 or both. Okay, we also found that the force between these two objects is inversely proportional to their distance squared. Okay, so F is inversely proportional to R square, where R is the distance between these two objects. Okay, because of this universal law of gravitational, the Newton's laws of universal gravitation, also called inverse square law. Okay, inverse square law because of this part of the equation. Okay, because the force is inversely proportional to the square of the distance. We call this law also the inverse square law. Okay, so when we combine these two equations, okay, we can write another equation. So another equation will be something like this: m1 m2 r square, but I want to write an equation, not just the proportional sign. Okay, so if I want to remove this, we need a proportionality constant, and the proportionality constant is uppercase G. Okay, and this is different than the lower gravitational acceleration. Okay, so you know that we use this symbol to represent the gravitational acceleration, but this is uppercase, and this uppercase is different than the lowercase, and we call it, okay, we call it universal we call it universal gravitational constant. Okay, universal gravitational constant. Okay, so here somewhere I have the number. Okay, so universal gravitational constant. Okay, G is called the universal gravitational constant. So I will come back here later, but let's see what else we have here. So this law, we call it the Newton's laws of universal gravitation, and it says that each object is two object, I mean, in this universe attract each other. Okay, or in other word, we can say that every particle in the universe attract every other particles with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. Okay, so you already see that. Okay, so that means every object in this universe, not only in this world or not only in this classroom, okay, every object in this universe attract every other object, and the magnitude of the force is this: F equal to m1 m2, which is the mass of these two objects, and r is the distance between the two objects, and the gravitational constant, universal gravitational constant. So we call it universal gravitational constant because it is valid everywhere in this universe. Okay, for example, the value of the gravitational acceleration is 9.80 meter per second square on the surface of Earth, but if you go to the surface of the Mars, it is approximately 3.70 meter per second square, which is different for Mars. Okay, so these are not universal constant, but this gravitational constant, this later I'm going to show what is the number. This is universal gravitational constant. It means that no matter where you are in this universe, the value of this universal gravitational constants always the same. Okay, so what is the value? So we determined it experimentally, and it is constant universally, and the value of the universal gravitational constant is 6.677 times 10 to the power minus 11 Newton meter square per kilogram square. Okay, now before I move to the next topic, let me show you this simulation. Okay, it's basically the same thing what I just talked. Okay, but I think simulation helps you to understand little bit better way. Okay, so here we see that we have two objects, m1 and m2. Okay, now the force by which m1 attracts m2 is this number. Okay, so this Newton. Okay, and you see that m2 attracts m1 with exactly equal amount of force. Okay, so when we have two objects, okay, one object attracts other, okay, by the same amount of force, okay, but in the opposite direction. The direction will be opposite. So this attracts this one, and this one attracts this one. The magnitude is always determined by using this equation. Okay, but for this object the direction is in this direction, and for this object the direction is this direction. Okay, that's why they are attractive force. Okay, and if you remember, the statement says that every object in this universe attract every other object. Okay, this is attractive force. All right, now if we as I mentioned earlier, that if we increase m1 or m2, we can increase these values. Okay, so let's see, if I increase the value of the mass 1, whether it increase or decrease. Okay, so you see that it is increasing, right? If you increase mass 2, you will see also it in also the value of f will increase. So you see that. Okay, all right, now what happen if I increase the distance between the two objects? Okay, so the distance now is 1. Okay, so distance now is 4 meters. Okay, so if I increase, so you see that it is decreasing. Okay, so if I increase the distance, okay, it will decrease. So you see that now it is 155. So if I increase, you see that it is decreasing. So it is decreasing because the distance is inversely, I mean the force is inversely proportional to the distance square. So when you increase the distance, the force will decrease. If you increase the mass, the force will increase. Okay, and if you want to increase by changing the distance, then you have to decrease the distance. So you see that now it is increasing. Okay, so I mean the arrow also shows about the length or the magnitude of the force. Okay, so you see that when you decrease, the arrow increase. When you increase the distance, arrow decrease. All right, so that's basically the Newton's law of universal gravitation. Now let's go back to our study guide and let's see what else we have there. All right, now this one, so gravity near the surface of Earth. Okay, so here this picture basically tells everything. So let's say if we talk about this, if let's say the apple is somewhere here. Okay, let's talk about this apple. Okay, now if the mass of the apple is m, the gravitational force will be something like this: Fg equal to mg, right? Now that we already learned from chapter 4. But now if I want to know what is the gravitational force using the Newton's universal law of gravitation, what would be the equation? So the equation will be something like this: the gravitational constant, universal gravitational constant, the mass of the apple, and here we have to use the mass of the Earth. Okay, and then the distance from the center of the Earth, okay, to the apple. Okay, now you know that that will be r square, I mean the radius of the Earth. So if it is very close, if the apple is very close to the surface of the Earth, okay, normally it is like in few meter, okay, then we can neglect this distance. Okay, we can neglect I mean we can neglect this distance. Why we can neglect this distance? Because this is few meter. Okay, this is few meter. On the other hand, from the center of the Earth to the surface of the Earth is huge distance. It is the radius of Earth is this kilometer, 6380 kilometer. Okay, so it is too large number compared to 1 meter, okay, or 2 meter or few meters. Okay, so because of this, we basically neglect this distance, and the equation is this, where me is the mass of the earth and re is the radius of the earth. So when an object is on the surface of earth, very close to the surface of earth, then we can use this equation to calculate the gravitational force, or this equation to calculate the gravitational force. Okay, both basically I mean you can use. Okay, for example, if you know the gravitational acceleration and the mass, you can use this, which is easy to use. If you want to if you know the mass of the earth, radius of the earth, and then the gravitational constant, then you can use this equation. Okay, but both basically tell you the same information. All right, now we have two equations for the same thing. We can equate and see what we get from equating them. Okay, so this is one equation, this is another equation, because they are basically the same info. They tell you the same information about the same information. We can equate them, and by equating them we get something like this. And then if we cancel m and m, we get an equation for the gravitational acceleration. Okay, so the gravitational acceleration is equal to universal gravitational constant, mass of the earth divided by radius of the earth square. Okay, so if I want to know the if I want to calculate the gravitational acceleration of any planet, okay, we can use this equation. Although here I derive this equation for earth, it is useful for any planet. For example, if I want to know what is the gravitational acceleration for moon, for example, so what we have to do, this is constant, we have to change the mass to mass of moon and the radius to radius of moon. Okay, so if you do that, then this equation basically give you the gravitational acceleration for the moon. If you want to do the Mars or any other planet, what you have to do, you have to just need to know what is the mass of that planet and what is the radius of this planet, and then plug in this equation. Okay, all right. Now by using this equation, you can determine the mass of the earth. Okay, so as I mentioned that the radius of the earth is 6380 kilometer. Okay, and we already know the gravitational constant, universal gravitational constant. We know that the gravitational acceleration. So by plugging these values here in this equation, you can calculate the mass of the earth. Okay, so here you see that we plug the value of, so here this equation, I solve it. So if you solve this equation for the mass of earth, you get this equation, and then gravitational acceleration is 9.80, radius is this kilometer. Okay, so kilometer means you have to convert it into meter. So by using this factor, I convert it into meter. Okay, so here this is a typo. Okay, and then the gravitational constant is this. Okay, 6.67 times 10 to the power minus 11 Newton meter square per kilogram square. Okay, so then if you plug these values in your calculator, it will give you this value. So the mass of the earth is 5.98 times 10 to the power 24 kilogram. Okay, all right, so this is a useful equation we can use for many to determine many things. Especially this equation is important to determine the gravitational acceleration. Okay. All right. The next thing is the circular orbits and satellite and weightlessness. Okay. So in the last lecture, you already see this simulation. Let's go back to that simulation. Okay. And let's try to understand what is the speed of this satellite. So this is the International Space Station, let's say. Okay, so one of the satellite. So what is the speed of this satellite, and what is the time period? That means how long it takes to travel one orbit. Okay. Yeah, basically these two things I want to know. And also in one problem, in the problem solving class, you will be learning about what is the gravitational acceleration at this point. Okay, so here you see that if the satellite is very close to the surface of the earth, that is basically 9.8 meter per second square. But because the satellite, the International Space Station, is not very close to the surface of earth, from here to here it's basically 400 kilometers. Okay, we cannot neglect these. Okay, so if something is not very close to the surface of a planet, what is the acceleration due to gravity over there? So in one problem we are going to also do that, but here in this theory section you are going to learn about what is the this satellite's speed and what is the time period. Okay, that's basically the two things. And in problem solving we will be exploring more on that. Okay. All right, so let me go to the simulation. Okay, so we already see this in last class. So so here's the satellite. Actually, let's use this one. Okay, so here you see that okay, so this is the satellite is moving, traveling in a circular path, although it's not circular. I mean, in real life it's not circular. Okay, and from the center of the circle, center of the earth, it's not just the radius of earth, right? We have to, when you deal with this kind of problem, we have to remember that it is about some distance from the surface of the earth. Okay, for example, for International Space Station, it is about 400 kilometers. Okay, all right, so this you already see in the last class, so I'm not going to discuss more about that. Let me go back and then try to tell you about the mathematics. Okay, so yeah, now when the space station somewhere here, right? So we know that the gravitational force between the earth and the satellite is this, right? Mass of the earth, m is the satellite's mass, and then this is the distance from the center of the earth to the satellite. So remember that here we have to be very careful. So this is this distance. Okay, many students just substitute the value of the radius of earth. Okay, but this is not the radius of earth. It's from the center of the earth to the center of, basically the center of the satellite. Okay, so for example, the radius of Earth is 6380 kilometer, and then the space station is at around 400 kilometer from the surface of Earth. So this radius is this. Okay, 6380, about 6,780 kilometer. Okay, make sure you understand this. All right, so this is the the gravitational force between the satellite and the Earth. And you know that because it is in a circular orbit, okay, this gravitational force basically act as a centripetal force, because the direction of the of this force is to the center of the circle, to the center of this circular path. Okay, so this is the, although it is the gravitational force, this is the centripetal force in this case. Okay, so then if we equate this equation with the centripetal forces equation, if you remember, the centripetal forces equation is this, right? So if you equate these two equations, you can find an equation for the orbital speed, I mean the equation for V. Okay, so let's see what we get here. So here you see that m and m cancel out. Okay, one of the r is also cancel out. So what we have here is basically v square equal to the gravitational constant, universal gravitational constant, the mass of Earth, and this radius. I mean, this is not the radius, it is from the center of the Earth to the satellite. Okay, so because this is the equation for the v square, to get v, we have to just square root, we have to take the square root of it. So v is this equation. Okay, so this equation tells us about the speed of the satellite. Okay, so in a problem class, we determine the speed of one of the satellite. Okay, and you probably determine more in the homework. All right, now so yeah, so you see that this is the equation we just derived, and then v will be, I mean, v orbit is square root of it. V orbit is basically square root of this, which you see already. All right, so the next thing is the time period. Okay, so what is the time period? So it's basically very similar to what we use in last lecture. Okay, so because it is a uniform circular motion, that means it is moving in this circular path. Okay, if an object starts from here, okay, so in one turn, in one full turn, it travels this distance, right? And this distance is basically oh yeah, so here I forgot the space. So this is the distance travel in one orbit and the travel time. So here should be some space. Okay, so this is the distance and this is the travel time, and you already know that the distance is the circumference of this circular path. Okay, and the circumference will be 2 pi r. So here you see this 2 pi r, and travel time for one full turn is the time period. So this is the equation, and from the last slide we already know that v orbit is equal to square root of the gravitational constant me over r. Okay, so substitute this here, and then 2 pi r t is still there. Now because we have a square root here, so let's square both sides. Okay, let's square both sides. So what we get, so when you square both sides, the square root goes away. Okay, so in the left hand side we have this, on the right hand side we have 2 pi square means 4 pi square and r square over t square. Okay. So if you simplify this equation for t square, okay, you get this. Okay, let me do it here. So you square both sides, you get this equation. Now you simplify this equation for, I mean, you solve this equation for t square. So if I multiply both sides by t square, we get something like this: t square me r equal to 4 pi square r square, and then let's divide both term with this equation. So we'll get 4 pi square r cube. Okay, so this is the equation for time period. Okay, now this equation we'll be using to solve some problem. Okay, so this is the equation for time period. So you see the square of the time period depends on the distance, okay, where the orbit is from the planet, okay, from the center of the planet. So this means the center of the planet to the satellite, and also the mass of the earth and the universal gravitational constant. Okay, all right. Now the last thing I'm going to talk is something called a geostationary satellite. Okay, and geostationary satellite is what whose time period is 1 day. Okay, so time period for a geostationary satellite is 1 day or 24 hours. Okay, so where we use geostationary satellite? Okay, so here is the definition of geostationary satellite. A geostationary satellite is one that stays above the same point on the Earth, which is possible only if it is above a point on the equator. Such satellites are used for TV and radio transmission, for weather forecasting, and as communication relays. Okay, time period needs to be equal to 1 day or equal to 24 days, 24 hours. Why we need 1 day or 24 hours? Because you know that Earth spins around its axis in 1 day or 24 hours. So geo means it is stationary with the Earth. Okay, so if we want something stationary with Earth, its time period should be equal to the Earth's time period. Okay, because Earth spins one full spin in 1 day or in 24 hours. For the geostationary satellite, we need similar time period or same time period. Okay, because of this, the geostationary time period is 24 hours. Okay, now let me show you the simulation, and then that's it for today. Okay, so here you see geostationary satellite near America. Okay, so here you see that the satellite is somewhere here. So this is the satellite near US. Okay, now let's see what happened. So here you see that the time period. So our goal is to check the time period. That means starting from here and coming back here, how long it takes. Okay, so let's see. So you see that, I mean, I was a little late. So you see that it takes like 24 hours, okay? Because we are a little off now. Where is the satellite? Yeah, so whatever, I just actually, yeah, so it was something like this. So because we are little off, that's why it's showing 24.6 hour, but it's basically 24 hours. Okay, and one thing you probably see that the satellite is always on top of the United States. Okay, I mean, not United States, is on top of the America. I think this is by some, yeah, so you see that it is South American. Yeah, it's probably South American satellite. Okay, it's always, when it rotates, I mean, when it travels in the circular path, it's always on top of on top, I mean, on top of the South America. Okay, so see that the earth is rotating. Okay, I mean, earth is spinning, and the satellite is also traveling in the circular path, but it is always stationary with respect to the earth. So that's why we call it geostationary. Geo means earth, and stationary means at rest with respect to earth. Okay, all right, so that's it for today. I'm going to stop it here, and in next class we are going to solve some of the problems.